If you have ever been stuck in gridlocked urban traffic, look, you know that exact soul-crushing feeling. You're just sitting there, hands gripping the steering wheel, right? Staring out at this endless sea of glowing red brake lights.
Oh, yeah, absolutely. It's brutal.
It is. And the exhaust fumes are like shimmering over the asphalt, and that aggressive horn honking from 3 lanes over is just starting to give you a massive migraine.
Right. And you find yourself just, looking up through the windshield at the open sky.
Exactly. And in that desperate moment, you probably daydream about a magic button on your dashboard. Something that would just let your car lift off the ground, float over the chaos,
Yeah.
bypass the miles of congestion entirely, and just glide directly to your destination. We've all been there. I mean, it's the universal modern fantasy for any daily commuter.
It really is. And, it stems from the fact that we are fundamentally terrestrial creatures, which means our first instinct has always been to build terrestrial infrastructure. We pave roads, we bore tunnels, we lay down steel rails.
Yeah, we build on the dirt.
Right. But urban space is finite. When that two-dimensional grid inevitably locks up, when you literally run out of square footage on the ground, the only logical direction to look is the third dimension. We just have to look up.
And today, we are taking that daydream, that fantasy of just floating over the traffic jam and looking at how it is becoming a very real, incredibly functional reality for millions of people.
Oh.
But we aren't talking about flying cars here or, autonomous drones or some sci-fi jetpack.
No, not at all. We are talking about a technology that most people probably associate with snowy mountains, heavy winter coats, hot cocoa, and ski resorts.
Yeah, ski lifts. Today's deep dive is all about the urban aerial cable car. We are going to explore how the humble gondola is absolutely revolutionizing mass transit in some of the most congested, complex, and mountainous cities on the entire planet.
It's fascinating because it requires a massive shift in perspective, to see a ski lift as a subway system.
Yeah, I bet.
For decades, the cable car was viewed almost exclusively as recreational infrastructure, or perhaps like a novelty tourist attraction at a scenic viewpoint. But when you start to analyze the severe urban planning challenges of the 21st century, particularly in rapidly expanding emerging economies, you realize this technology solves some incredibly complex geographical and socioeconomic puzzles.
Puzzles that traditional transit just can't handle, right?
Exactly. Traditional subways, light rail, or bus networks simply cannot touch these areas due to extreme cost or just the physical punishing terrain.
So, to really get to the bottom of how this works, we've pulled together an incredible stack of data today, and we're going to be pulling insights from a massive World Bank report that analyzes the financial and social impact of urban aerial cable cars across Latin America.
That report is incredibly comprehensive.
It really is. We're also going to get into the hardcore physics using a deeply technical academic master's thesis from UMIT Tyrol University in Austria. I mean, they actually built 3D printed sensors to measure how these cabins swing in turbulent weather. It's wild stuff.
It's amazing research.
Yeah. And we've also got the actual technical specifications and safety manuals from industry titans like Doffelmayer, an abstract from the OITAF Congress breaking down the environmental life cycle of these systems, and a really powerful report from the World Resources Institute on Urban Transformation.
What makes this collection of sources so compelling to me is how they force us to look at a single piece of infrastructure from completely disparate angles. I mean, we have the macro level urban planning and multi-million dollar economics on one hand,
Right.
but we also have the micro level engineering. We are looking at the exact design of the mechanical grips, the accessibility features for a passenger in a wheelchair, and real-time wind sensors. It all has to work perfectly together for the system to be viable at all.
So rather than just looking at the nuts and bolts right out of the gate, let's start with the human element, the urban planning revolution. Because, before you string a massive wire through the sky, you have to have a desperate need on the ground. And to tell this story, we really have to go back to the year 2004, to a city that fundamentally altered the way the entire world looks at public transit. We really need to talk about Medellin, Colombia.
Yes. The inauguration of the metro cable in Medellin in 2004 is widely considered the watershed moment for modern urban transit. It was the first cable car in Latin America, and arguably the world, that was specifically engineered and integrated into a city's broader mass transit network rather than just functioning as a standalone tourist ride.
Before 2004, Medellin looked at their map and saw a monumental problem. You have this vibrant, economically active downtown area situated way down in the valley. But then you have these sprawling, incredibly densely populated hillside neighborhoods rising up on either side.
Places like Comuna 13, right?
Exactly, Comuna 13. These are historically marginalized low-income communities, and
Yeah.
the physical geography there is just brutal.
The steepness of the terrain in those peripheral neighborhoods simply cannot be overstated. Over the previous decades, these settlements expanded rapidly and largely informally.
Meaning no central planning.
Right. They were constructed without a centralized master plan. There were no wide avenues reserved for future rapid transit buses, no grid systems, no gentle switchbacks. It is just a labyrinth of narrow, winding, almost vertical streets, alleys, and endless staircases built directly into the side of a mountain.
Let's try to put ourselves in the shoes of someone living up in one of those hillside neighborhoods before the metro cable existed.
Yeah.
Your job, the grocery store, municipal services, they're all down in the city center. What does your morning commute actually look like on a random Tuesday?
Well, it was a daily ordeal that actively hindered economic mobility. According to the data in the World Resources Institute report, a trip from these high peripheral hillsides into the valley floor could easily consume 2 hours each way.
2 hours. Wow.
Yes, you would start by walking down treacherous, poorly lit staircases, often in the rain. Then you would wait to catch an informal, privately operated minibus. And that bus has to navigate those congested, narrow, winding roads, constantly getting stuck in traffic.
Just a nightmare.
Right, and then you would likely have to transfer to a different bus line halfway down, paying a second fare, and then finally pay a third fare to get onto the mainline metro system in the valley.
So you are losing 4 hours of your day, every single day, just sitting in traffic or walking up and down steep stairs. And you're paying multiple different transit fares out of a daily wage that is already stretched incredibly thin.
Exactly.
If a job takes 2 hours and a significant percentage of your income just to reach, I mean, you are effectively cut off from the formal economy of your own city.
Urban planners often refer to this as a geographical poverty trap. The physical isolation breeds economic and social isolation. You are technically a resident of the city, but you cannot access its resources. But then the city introduces Metro Cable Line K.
And the impact observed in the WRI and World Bank reports is just staggering. That 2-hour, multi-fare, exhausting nightmare drops to a smooth 30-minute aerial trip.
And the most important part of that 30-minute trip isn't just the time saved, is it? It's the ticket.
Yes. The fare integration was the absolute masterstroke here.
Right. When a commuter swiped their transit card to enter the Metro Cable station up on the hillside, that single fare covered the entire journey. They hopped on the gondola, glided over the gridlock, arrived at the valley floor, and walked directly into the mainline subway system without ever pulling their wallet out again.
By doing that, Medellin essentially shrank the city.
Right.
You subsidized the geography. And looking at the ridership numbers from the World Bank report, I mean, this wasn't some niche pilot program. In 2019, the Metro Cable network moved 15.9 million passengers.
That is a vital, load-bearing artery of a major metropolis.
It really is. It proved the concept so definitively that municipal governments all around the world started looking at their own congested mountains and ravines. They realized they had been ignoring the airspace right above their heads. Which brings us to the most extreme, scaled-up version of this concept on the planet, La Paz, Bolivia.
Oh, La Paz is incredible. If Medellin was the proof of concept, La Paz took the idea and turned it into an absolute behemoth. The geography of the La Paz metropolitan area makes Medellin look relatively tame by comparison.
Right, because you have the city of La Paz itself sitting down at the bottom of this steep canyon at an elevation of about 3,650 meters. For context, that is roughly 12,000 feet above sea level. You are literally already in the clouds.
You are.
But right next to it, perched on the edge of the high plateau directly above the canyon, is the city of El Alto.
And the demographic explosion of El Alto is a crucial piece of context here. The World Bank report notes that El Alto was only formally designated as its own city in 1987. Back in 1950, it was just a small settlement with about 11,000 residents.
Oh, wow, so it grew fast.
Incredibly fast. Today, the population is well over 1 million. It holds the title of the highest major city in the world, sitting at a breathtaking 4,070 meters, so over 13,300 feet.
So you have this massive, rapidly expanding population up on the plateau in El Alto, and the vast majority of them need to travel down into the canyon to La Paz for work, healthcare, and commerce. The sources mention a daily commuter base of roughly 440,000 people trying to move between these two cities every single day.
It's a massive logistical challenge.
Yeah, and they are separated by a sheer 400-meter drop in elevation. I mean, a literal cliff.
Attempting to move nearly 500,000 people up and down a 400-meter cliff using surface transport is a nightmare. You have a few winding arterial roads connecting the plateau to the canyon. The traffic jams were legendary, sometimes adding hours to a trip that should technically take minutes.
I can't even imagine the emissions from that.
That was a huge issue. The pollution from thousands of idling diesel buses and cars at that extreme altitude where the air is already incredibly thin created a severe public health crisis. And traditional solutions were totally off the table. You cannot realistically or economically bore a multi-billion-dollar subway tunnel up the face of a 400-meter cliff.
So in 2014, they launched Via Teleferico. And they didn't just build one little line to test the waters, did they?
Yeah, they went all in.
They built an entire web. Today, it is the most extensive urban cable car network in the world. They have 10 different lines, color-coded just like the London Underground or the New York subway map, covering over 30 kilometers of aerial network. They're moving an average of 160,000 passengers every single day.
It functions exactly like a subway system, but they avoided the billions of dollars and decades of construction required to tunnel through solid bedrock. They just claimed the empty airspace.
It's brilliant.
But, the World Resources Institute report highlights a critical lesson from both Medellin and La Paz. The ultimate success of these mega projects hinges on far more than just laying concrete and stringing up a wire. The most difficult obstacle wasn't the engineering, it was community trust and human psychology.
I am so glad we are touching on this because it's so easy to look at the shiny gondolas and forget the context of the neighborhoods they were actually built in. Think about a place like Comuna 13 in the early 2000s. You have a community that has suffered from decades of severe neglect, a complete lack of basic municipal services, and extreme traumatic violence. The community was highly fragmented.
Exactly. You cannot simply drop a massive futuristic piece of infrastructure worth tens of millions of dollars over the roofs of a neglected neighborhood and expect the residents to immediately embrace it. There is an inherent and, frankly, entirely justified skepticism.
Yeah, they must have been so suspicious.
The WRI report details how residents initially questioned the motives. They wondered if the massive concrete towers were going to cause their hillside homes to collapse. They feared it was a gentrification ploy designed to displace them.
I can completely understand that reaction. I mean, imagine living somewhere where the city hasn't bothered to fix the potholes or provide reliable trash collection for 20 years, and suddenly there are government surveyors in your alleyway saying they're going to fly spaceships over your roof. How does a city actually overcome that level of entrenched distrust?
It requires grueling, ground-level human interaction. Before the first concrete was ever poured for Line K, the Metro de Medellín Transit Authority sent teams of social workers out into the hillside neighborhoods.
Just to talk to people.
Yes, and this wasn't just a matter of handing out glossy flyers or hosting a single town hall meeting. They went door to door. They ran community workshops. They gathered granular data on how people actually lived, where they traveled, and what they feared.
That is some serious dedication.
They painstakingly explained the mechanics of the system, how it would benefit the local economy, and how to use it safely. The WRI report documents that these social workers engaged in direct conversations with over 40,000 individuals.
40,000 individual touchpoints. That is a massive administrative undertaking. But it sounds like it was absolutely essential to prevent the project from being sabotaged or just rejected by the very people it was meant to serve.
It was the only way to overcome the historical fragmentation. Because of that effort, the community began to feel a sense of ownership over the metro cable. It was no longer an alien object imposed upon them by distant bureaucrats in the valley. It became their transit system. Planners refer to this phenomenon as redefining a city's psychological borders.
Psychological borders is such an evocative term. How does a physical cable car alter the psychology of a neighborhood?
Well, think back to the 2-hour commute. If it takes you 2 grueling hours to reach the downtown core, downtown feels like it belongs to a different world. It feels inaccessible, reserved for a different class of citizen.
Yeah, you just never go unless you absolutely had to.
Right. That physical isolation breeds a deep psychological and social isolation. But when you compress that journey into a smooth, scenic 30-minute ride, suddenly the city center is yours too. You are integrated into the formal, bustling life of the city. You become a visible, active participant in the wider urban ecosystem. It strengthens social cohesion in a way that economists struggle to quantify, but that sociologists consider absolutely invaluable.
And beyond the psychology, there's a very tangible physical aspect to this integration. The World Bank report emphasizes a major advantage of cable cars over expanding surface roads, their incredibly minimal physical footprint on the ground.
This is a vital urban planning consideration. If a city decides to expand a rapid transit bus route into a dense, informally built hillside neighborhood, they inevitably have to bulldoze dozens, if not hundreds, of homes just to widen the street.
Right, the displacement would be huge.
It causes massive, painful displacement and destroys the existing social fabric. A cable car, conversely, operates in the airspace, which is unused real estate. On the ground, it only requires a small footprint for the station building and a few square meters here and there to plant the steel support towers.
And from what I was reading, the space they do use often becomes a massive upgrade for the neighborhood. They don't just build a sterile transit station, they reclaim the public spaces beneath the lines. In Medellin, they built libraries, public plazas, and small parks around the stations. The infrastructure project actually became a vehicle to inject high-quality, safe public spaces into areas that desperately lacked them.
This station evolves into a community hub. It is a remarkably elegant solution to a messy, seemingly intractable urban problem.
Okay, so the urban planning logic is rock solid. You secure community buy-in through intense social work, you build the stations without bulldozing the neighborhood, and you successfully redefine the city's borders. But from my perspective, that is really only half the battle. Because once those 160,000 daily commuters actually show up at the stations in La Paz, the system has to safely, efficiently, and comfortably load them into moving boxes in the sky.
That's where the engineering takes over.
Exactly. And we aren't just talking about able-bodied commuters with perfect balance here. We are talking about grandmothers, people using wheelchairs, parents wrangling baby strollers, and people carrying heavy groceries.
Which brings us to the hidden engineering marvel that actually makes modern urban cable cars viable for the general public. Because if you simply installed an old-school, fixed-grip ski lift in a city, it would be a complete disaster. It simply cannot handle the accessibility requirements of mass urban transit.
So let's dive into the mechanics of this. We are relying heavily on the technical specifications and engineering documents provided by Doppelmayr, one of the leading manufacturers in the global cable car industry. First off, just to visualize this, how big are these urban cabins?
The capacity varies depending on the specific system design and the projected passenger volume, but the cabins typically accommodate anywhere from 4 to 15 passengers. The gold standard for many of these high-volume urban systems, like those deployed in La Paz and Medellin, is the 10-passenger monocable gondola.
Okay, just to clarify the terminology for everyone, when we say monocable, we mean there is one single continuous loop of braided steel wire rope that does two jobs simultaneously. It supports the physical weight of the cabin, and it pulls the cabin along the line.
That is accurate. One massive, continuously moving loop of steel. And the overall transport capacity of a well-engineered monocable line is astonishing. According to the specs, they can safely move up to 3,600 passengers per hour per direction.
Okay, let's do the math on 3,600 passengers an hour. If you are using 10-person cabins and you're running at maximum capacity, that means you need 360 cabins arriving at the station every single hour. Divide that by 60 minutes, and you have a cabin pulling into the station every 10 seconds.
It is a continuous high-frequency flow. This is a massive advantage over trains or buses. You rarely have to consult a timetable or wait 15 minutes for the next train on an urban cable car network. You just walk into the station, and the next cabin is already there, waiting for you.
But this is where my brain really starts to struggle with the physics of it. If that main steel cable is moving fast enough to transport thousands of people over mountains, let's say it's cruising at, what, 20 or 25 kilometers an hour?
Yes, around that speed.
How on earth do you load a person in a wheelchair into a cabin that is flying by every 10 seconds? If the cabin stays attached to that fast-moving wire, it seems like boarding would be a terrifying, highly dangerous experience.
Well, if the cabin remained permanently attached to the cable at full cruising speed, it would be physically impossible to board safely. And that exact dilemma is why the detachable grip technology is the absolute core innovation of this entire transit revolution. It is the operational genius that takes a recreational mechanism and transforms it into a viable, stress-free mass transit solution for all demographics.
I really need you to break down this detachable grip for me, step by step, because the idea of a cabin just letting go of the wire while suspended in the air sounds terrifying. How does this mechanism actually work?
Let's visualize the main wire rope as a massive, continuously moving conveyor belt that stretches across the city. It never stops and it never slows down. The cabin is attached to this rope by a highly complex mechanical grip located on the roof. Think of it as a heavy-duty, spring-loaded steel jaw.
Okay, a steel jaw on the roof.
Right. While the cabin is out on the open line traveling between stations, that jaw is clamped fiercely shut around the moving rope. The cabin is carried along at the exact same high velocity as the wire.
Okay, I am with you so far.
Yeah.
High-speed cruising over the city.
But the critical sequence begins when the cabin approaches the station. As it enters the enclosed station terminal, a physical stationary rail mounted in the ceiling of the station engages a lever on the cabin's grip. This mechanism forcibly compresses the springs and opens the jaw. The cabin physically lets go of the fast-moving wire rope.
Wait, so it just drops? How does it not plummet or just smash into the station equipment?
It doesn't drop because at the precise microsecond it releases the main rope, a set of small nylon reels located on the top of the cabin's grip mechanism roll onto a separate internal steel track suspended within the station.
Oh, I see.
The cabin is now hanging from this internal track, completely decoupled from the main pulling wire. But it is still moving at 20 kilometers an hour due to its own momentum. This is where the deceleration system takes over.
How do you safely brake a heavy cabin that just came flying into the station off a wire?
Above that internal steel track, there is a mechanism called a tire conveyor. It is essentially a long row of rubber tires mounted in the ceiling, looking somewhat like a horizontal assembly line. As the cabin rolls onto the internal track, a flat metal friction plate on the top of the grip makes contact with the spinning rubber tires.
Okay, so the tires grab the top of the cabin. But if the tires are spinning, doesn't that just keep the cabin moving fast?
The brilliance is in the gearing. The first tire the cabin hits is spinning very fast, matching the 20 km/h speed of the cabin. But the next tire in the row is spinning slightly slower, and the next one is slower still.
That's so smart.
As the grip passes from tire to tire, each subsequent tire physically forces the cabin to slow down, acting as a progressive braking system. It smoothly and safely decelerates the cabin from highway speeds down to a literal crawl, often less than 1 km/h.
That is incredible. It is exactly like taking an off-ramp on a highway. You are cruising at 60 miles an hour, but you decouple from the main flow of traffic, take a separate ramp, and use your brakes to slow down to 5 miles an hour so you can pull into a parking spot. And meanwhile, the rest of the highway traffic behind you just keeps flying by at full speed.
That analogy captures the mechanics perfectly. By the time the cabin reaches the actual passenger loading platform, it is barely creeping along, and this drastic reduction in speed is where the crucial accessibility features come into play.
Because the cabin is moving so slowly, the doors can open fully, and there is absolutely no rush.
Precisely. Doppelmayr specifications highlight that this slow speed zone allows for what they call completely level access boarding. The floor of the slowly moving cabin is engineered to be perfectly flush with the concrete platform of the station. There is no step up, there is no dangerous gap to trip over.
That completely changes the demographic of who can use the system. If you are a non-skier, if you are an elderly resident with mobility issues, if you use a motorized wheelchair, or if you are a parent pushing a heavy double stroller, boarding is completely stress-free. You don't have to perfectly time a leap onto a moving platform. You simply walk or roll right into a wide-open room that just happens to be moving sideways very slowly.
The technical sources also point out that this level, slow-speed access is robust enough to allow for the transport of standard Euro pallets.
Wait, really? Like freight?
Yes. This means that municipal light freight, cargo, and commercial deliveries can be integrated directly into the passenger transit flow during off-peak hours. It also easily accommodates alternative equipment like bicycles. It thoroughly democratizes the transport infrastructure.
And I assume the entire process just runs in reverse when it's time to leave the station.
Exactly. Once the passengers are loaded and the automated doors close, the cabin enters the acceleration zone of the tire conveyor. The tires progressively spin faster and faster, pushing the cabin along the internal track until its speed perfectly matches the velocity of the main wire rope.
And then it just clamps back on.
At that exact moment, the spring-loaded jaw clamps back down onto the wire, and you are seamlessly fired out of the station at full cruising speed. Decoupling the high travel speed from the slow boarding speed is the fundamental engineering key to urban aerial transit.
It is brilliant engineering. But what about the stations themselves? In cities like La Paz or Medellin, you are building incredibly dense, tightly packed neighborhoods. You don't have the luxury of clearing city blocks to build sprawling, airport-sized terminals.
The spatial constraints are severe, which is why the station engineering is highly modular. Doppelmayer's documentation emphasizes that the massive drive machinery, the enormous electric motors, and the giant bull wheels that actually pull the continuous loop of cable can be configured to fit the available footprint.
How so?
Well, if ground space is at a premium, the machinery can be located overhead, built directly into the roof of the station. If vertical space is restricted, it can be housed in subterranean concrete vaults underneath the station.
That modularity is key. But here's a logistical question that just popped into my head. What happens at night? When the transit system shuts down at 11:00 p.m., where do all these hundreds of 10-passenger cabins go? Do they just leave them hanging out on the wire over the city until morning?
Generally, no. Leaving the cabins exposed on the line subjects them to unnecessary weathering, wind stress, and potential vandalism. This is where the detachable grip technology provides yet another massive advantage. Because the cabins can let go of the main rope, they utilize a patented dead-end rail parking system.
How does a parking system for a flying box even work?
Inside the station terminal or an especially built adjacent depot, there's a labyrinth of overhead storage rails. When the system shuts down, the cabins decouple from the main wire and are automatically routed onto these storage rails. They can be stacked practically end to end, requiring very little physical space.
Oh, wow. So it's like a massive closet.
Yes. The entire parking procedure can be operated manually, semi-automatically, or fully automatically. The operator can essentially push a single button, and the massive transit system systematically packs itself away into a dense, secure closet for the night.
It is so efficient.
Yeah.
But as you describe all these moving parts, the spring-loaded jaws opening and closing every 10 seconds, cabins transferring from high-speed steel ropes to rubber tires and back again day in and day out, my mind immediately goes to the catastrophic risks. What happens if one of those jaws doesn't close all the way? What if a spring is weak and it only grabs the wire halfway before the cabin gets launched out of the station?
The safety tolerances required for this are microscopic, and the industry knows it. The system utilizes incredibly sophisticated electronic and mechanical monitoring equipment. Every single time a grip opens or closes within a station, an array of sensors verifies the exact millimeter-precise position of the mechanical components.
What kind of sensors are we actually talking about?
A combination of optical sensors and physical mechanical limit switches. If a grip fails to close with the precise, mathematically required clamping force, or if the jaw is even a fraction of a millimeter out of alignment, the monitoring equipment detects the anomaly instantly.
And then what? Just flash a red light on a screen?
No, it doesn't just send a warning light to an operator. It immediately and automatically triggers the emergency braking system, halting the entire lift network before that compromised cabin can even leave the safety of the station building.
It just drops the hammer and shuts the whole thing down.
Instantly.
Yeah.
There is zero margin for error allowed. Furthermore, because these systems serve as primary public transit, operating 16 to 18 hours a day, 365 days a year, maintenance cannot be an afterthought. The modular station designs feature incredibly clear layouts, ensuring extreme ease of access for technicians. Routine maintenance on the grips and sensors has to be fast and flawless, which is why the components are designed to be easily reachable.
Okay, so I am convinced that the stations are highly controlled, remarkably safe environments. The grip technology is practically magical, the accessibility for wheelchairs and strollers is top-notch, and the safety sensors are watching every single millimeter of movement. But, and this is a big but, the moment that cabin leaves the station, it is no longer in a controlled environment. It is hanging from a steel wire hundreds of feet in the air, completely exposed and at the mercy of the elements.
And that exposure introduces an entirely new, highly complex set of engineering and operational challenges that simply cannot be solved by a sensor in